this is what you asked for, and physiology is, of course, at the basis of what everybody is interested in with regard to quantitative EEG. And so I thought it might be useful for us to review the basics of how the EEG is generated and some of the fundamental concepts about, at least about what we know concerning the relationships between neurotransmitters and various signaling pathways. So, I'm a medical school professor at American University of Antigua, College of Medicine, in Antigua in Barbuda in the West Indies. I'm retired from Howard University College of Medicine after 35 years in the same office. And at AUA, we call it, in Antigua, they made me an offer I couldn't refuse to spend time on the beach and teach. And so I'm working on my tan and teaching. Okay, concerning questions, everybody is available and open to asking questions at any time. So I hope you'll take advantage of that. I have no problem with stopping at any time and answering questions. Can everybody hear me?
We hear you fine, Rick. We hear you fine.
Yep,
okay.
Everything's good, Rick. Yep.
Okay, so give me some feedback occasionally because I feel like I'm talking to the wall here.
Yeah, it's an odd experience, isn't it?
Yeah. Well, it's very similar to talking to my students. These days, they're very passive. They're used to TV, not interactive TV. So here are the goals and objectives, which I think were distributed, what we want to accomplish, to understand the electrical basis of the EEG and all the technicalities of how ion channels and neurotransmitters are interacting to produce fast wave and slow wave, synchronized and desynchronized EEG recordings. And then if we have time, we'll get into sleep. I know that's Martin's favorite topic, and so he can help me with the sleep hygiene aspect of the physiology of sleep. So here is the dogma. This is what has been proposed for years and years and years as to what creates the EEG. We start up here at the top, and let's give you a laser pointer. Hold on. To look at. No? Can't bring up my... Oh, here we go. Can you see the laser pointer?
Yes. See it all right, Rick?
Yes, perfect. Yep.
Okay, very good. So here's my laser pointer. So we start up here, and these are pyramidal cells. Pyramidal cells are the main cell in the cerebral cortex, and basically the EEG is generated from the outer layers of pyramidal cells. And these are the ones that are closest to the scalp and the skull. And they're organized actually just like you see them here. They're actually perpendicular to the surface of the brain and the scalp. And they have these dendrites, which we know are the receiving end. And at the bottom, there are apical dendrites and there are basal dendrites, okay, projecting from these pyramidal cells. And so we find that the apical dendrites provide a source, and the basal dendrites provide a sink. Source and sink for what? For electrical charges. Now remember, in the brain, as all the body fluids, electrical charges are floating around as ions, sodium ions, potassium ions, chloride ions, all kinds of ions, positive and negative. And so when we have a predominance of negative ions in the extracellular fluid, that is around these cells, the fluids around these cells, we call it interstitial fluid. When it's negative here in the apical dendrites and positive here down at the basal dendrites, we produce a dipole. Dipole, meaning the two different poles, just like a battery, have two different sets of charges or net charges. And so we get a flow. We get a flow of current around these outer layers of pyramidal cells. So basically, pyramidal cell dendrite potentials are the source of the EEG brain waves. Now, if we look down here, I have a comment that each of these cells, not just here, all of these pyramidal cells are consisting of 30,000 excitatory inputs versus only 1,500 inhibitory inputs per cell. So there's a predominance of excitatory inputs. The inhibitory inputs, just whenever we have control over our cars, we have to have an accelerator and we have to have a brake. And so the inhibitory inputs are the brakes on these pyramidal cells. Otherwise, we would have overexcitation all the time, and we would have a condition of seizure and epilepsy continuously, which we know is abnormal. So what we have here are these stellate cells generating the main inhibitory neurotransmitter in the brain called GABA that produces the brakes. And these are those inhibitory inputs. Okay? So we have excitatory and inhibitory inputs. All right. That's wonderful. So where does the wind for the wave come from? You see, just like a surface wave on the ocean or in the sea, we have surface waves, but they have to be generated from somewhere. They don't just generate themselves. So basically, the wind that produces the waveforms comes from subcortical. So all this is in the cerebral cortex. But now, the subcortical areas. Subcortical areas include the thalamus, and the entire brainstem produces these inputs, excitatory inputs primarily, okay? Primarily excitatory inputs to the pyramidal cells, okay? And the pyramidal cells have outputs to those subcortical areas. So for example, if one of those subcortical areas is the thalamus. The thalamus is a structure that pre-processes all the information going to the cerebral cortex from the brainstem. And that is ascending information, information coming up, okay? So that's where the wind is coming from for these brain waves. Does that make any sense? The wind for the brain waves is coming from these subcortical structures, the inputs, mainly excitatory inputs, but some are inhibitory. Okay. Now, we have a balance. We have a fast accelerator and we have a slow accelerator. Obviously, we would associate a fast accelerator in the cortex with a high arousal state. So when a person is awake, so we have to differentiate between being awake and being asleep. Basically, right now, we're just talking about awake. We'll talk about sleep later if we have time. But in a high arousal awake state, we have these pyramidal neurons, and their neurotransmitter is primarily glutamate, the excitatory neurotransmitter. And in the cortex, from the subcortical areas, for example, from the thalamus, we have acetylcholine as the excitatory and possibly an inhibitory neurotransmitter. So an excitatory and an inhibitory neurotransmitter can be, or a single neurotransmitter can be excitatory or inhibitory depending on the receptor on the pyramidal cells. And so if the pyramidal cells happens to have an M1 receptor, M stands for muscarinic because it's excited by acetylcholine plus muscarine, which is an extract of poison mushrooms, it's excitatory. But if it's an M2 receptor on that cell, it's inhibitory. So acetylcholine can respond by exciting either M1 or M2 receptors, and it's the area of the brain, it's the particular pyramidal cell that determines what the response will be, whether it has a predominance of M1 excitatory or M2 inhibitory transmitters. So the glutamate and acetylcholine are generating primarily beta and alpha amplitude rhythms. Okay, the beta and alpha amplitudes are coming from these acetylcholine, we call them cholinergic neurons, projecting to the pyramidal cells, interacting with the pyramidal cells in the awake state, and we would call that high arousal. So we get fast activity in terms of beta and a little bit slower activity with respect to the alpha or the high alpha. Now, this is balanced by a low arousal wake state. So what happens when somebody is very attentive in a high arousal wake state? There's a predominance of what? Acetylcholine. And now, when we move to a low arousal awake state, we're not paying attention so much. We're getting, in fact, a little drowsy, perhaps. We're not going to sleep. I didn't mention sleep. This is just arousal or low arousal awake state. We then get a predominance of inputs from what we call the ascending reticular activating system that are coming via the brainstem area called the raphe, you might have heard of, that makes serotonin, and the locus ceruleus, which makes norepinephrine in the brainstem. And I'll show you some diagrams later which will show you these areas. So the low arousal awake state is predominated by serotonin, dopamine, and norepinephrine. Dopamine is primarily coming from the limbic system and the reward pathways of the brainstem, called the ventral tegmentum and the nucleus accumbens, and norepinephrine, as we said, from the locus ceruleus, and a little bit of dopamine from the locus ceruleus, but very little. So an abbreviation that I like to use for serotonin, rather than spell it out, is 5-HT, because serotonin is 5-hydroxytryptamine. So basically, it's the 5-hydroxytryptamine receptors, just like here we had M1 and M2 muscarinic acetylcholine receptors, that's organizing the beta and alpha amplitudes, the delta amplitudes, and we can include theta among them because they're the slower, it's the slower waves, but much less is known about theta, and theta is a little more complicated, and not, the story about theta isn't as consistent as it is for delta. So we're going to stick with delta for now. So these are serotonin receptors, and ADR stands for adrenergic receptors. Adrenergic refers to adrenaline, which are the norepinephrine and dopamine receptors. And these are alpha and beta adrenergic receptors. They're responding to norepinephrine and epinephrine. And then we have special dopamine receptors too. We're going to try to keep it simple and keep dopamine out of it, because dopamine doesn't play as big a role as norepinephrine is in creating these amplitudes or these waveforms. So generally, we can think of this as a balance between the cholinergic, and here we would call it the monoamines. So serotonin, dopamine, and norepinephrine all make up a class of compounds called monoamines. So we have a balance between cholinergic and monoamine inputs. Everybody with me, or did I put you all to sleep?
No, it's excellent. It's very good.
It's great.
Okay.
Yep. Good, good, good.
And so there is this monoamine balance hypothesis that says, at least in some brains, and we have to keep reiterating that not every brain is the same. So we can't always say that every brain is going to do this, but at least in some brains, and at least in the eyes closed resting state, that there seems to be some considerable information or considerable research that supports this balance hypothesis, that there's a balance between the acetylcholine or cholinergic and the monoamine inputs, meaning that when there's an abundance of the cholinergic, what do we have? A high arousal awake state, and when there's an abundance of the monoamines, serotonin, dopamine, and norepinephrine inputs, we move to a low arousal awake state characterized by more delta activity compared to, in the high arousal state, more beta primarily, and sometimes alpha. Okay. Wow. What the hell is this? This is an EEG up here. This is the EEG at 10 hertz. So we obviously have an alpha rhythm here. Okay? So this is what an EEG at 10 hertz might look like. And down here are the inputs from the thalamus. Remember in the previous slide, we said down here we have subcortical, meaning thalamus and brainstem, creating the wind, if you will, for the waves up here. Okay. So now we have the EEG, which are our waves, and down here, this is showing you what's happening in the areas that are producing the wind. Okay. We would call this a more synchronized pattern than what I'm going to show you here, which is a desynchronized pattern or a beta pattern. The beta pattern might be 25 hertz, and this pattern we already know. We identified it as 10 hertz. So what is the essential difference? The essential difference is in the thalamus, we see, and by the way, another name for EEG is thalamocortical oscillation, because there are dipoles set up not only in the pyramidal cells, but the oscillation of activity is occurring because of what's going on in the thalamus. So we call those neurons that are producing the oscillations thalamocortical neuron, and these are the membrane potentials. Now, this is not the same as the EEG. The membrane potential means we have to stick an electrode inside the cell itself. So we have to go into the thalamus itself and produce and stick a wire inside the cell and look at the potential or the difference in charge across the cell. We have to have an electrode in the cell and an electrode just outside the cell to record what we call membrane potential or the difference.
Rick,
these oscillations.
Clarification.
Yes.
Just to make absolutely sure I understand what you say. So now we are talking about thalamic electrical inputs, nerve signals, not about
yes. Neurons.
Yeah, okay, so I get it.
Yes. So to record something like this, you'd have to have a wire inside the cell and a wire outside the cell to see what's happening. And when we do that, when we find the right neurons, we see that they oscillate at the same frequency as the EEG. You see it down here? Now what makes them oscillate are these calcium spikes. And these calcium spikes can be considered like pacemakers. You know, the SA node, what we call the sinoatrial node in the heart, is the pacemaker for the heart. And so it generates its own electrical rhythms that keeps our heart going. And so this is working very similar to how the SA node in the heart would work. First of all, the key element is you need these hyperpolarizing afterpotentials. Now, let's say a normal membrane potential would be 70. You see where my marker is here at 70, or this is actually minus 70, because the membrane potential at rest is always in the negative range, minus 70. Beyond minus 70, when we go toward minus 90, is called hyperpolarization. We're inhibiting because we're getting further away from the threshold or firing line. In these neurons, their firing line appears to be around minus 60, which is right here. And when they reach minus 60, you get these spikes, okay? And these are action potentials. These action potentials are the ones that are propagated forward to the cortex, producing thalamocortical oscillations. So the requirement is that you need the hyperpolarizing after potentials. You have to go beyond minus 60, all the way down to about minus 85 in this case, before we generate this rhythm. You're going to see in a few minutes that if we don't have these hyperpolarizing after potentials, we don't get the calcium spikes, and we don't get this rhythm. We don't get this synchronized rhythm like we're seeing here that's at the same frequency as the EEG we're recording up here from the scalp. So what are the conditions in the body, in the brain, in the central nervous system that are necessary for a synchronized EEG? Well, first of all, the ARAS system. ARAS stands for Ascending Reticular Activating System. And what the Ascending Reticular Activating System is a pathway made up of several pathways, in fact, a super pathway, like a super highway with many lanes in it, that is bringing information to the thalamus, okay, to the thalamocortical neurons that we just saw. Where are they coming from? They're coming from the medulla oblongata. It's coming from the midbrain. It's coming from the hypothalamus. It's coming from all areas of below the cortex, what we call subcortical structures that, remember, I said, are producing the wind for the waves to occur. Okay. So when the ARAS system, remember, it's called activating system. It's activating the cortex. So when there's reduced activity in the ARAS system, what kind of state would we be in? Would we be in a high arousal awake state or a low arousal awake state? Clearly, it would be a what? Low arousal awake state. And that's when we start seeing more synchronization. Okay? Synchronization meaning higher amplitudes and lower frequencies compared to the faster desynchronized waves that are characteristic of beta and gamma oscillations. Okay. So in the thalamocortical neurons, here's what we see. We see an increased GK. What does G stand for? G means conductance of potassium. K is potassium. Conductance of potassium. And potassium is always conducted from inside to outside because there's more potassium inside cells than outside cells. When we do that, we get those hyperpolarizations I showed you earlier. These hyperpolarizing potentials. You see? And normally, the resting membrane potential should be about minus 60 to minus 70, but here they're going toward minus 90, maybe minus 80, minus 85. And that's generating these oscillations. Okay, slower oscillations with higher amplitude than the desynchronized wave. That's a signal for the calcium spikes with the action potentials. You see, the calcium spikes are local. The hyperpolarization is local in the thalamus. But now if we see an action potential, we know that's not local anymore. That's propagated all the way to the cortex. Okay? So these are some of the complications. And now when we have that hyperpolarization, we get the calcium channels opening up. G stands for conductance of calcium. Just like potassium is always conducted outward, calcium is conducted inward. And when we conduct calcium inward, we get the action potentials. Okay? V stands for voltage, means they're gated or they're activated by the voltage. What voltage? The voltage down here, the hyperpolarization, is actually activating the calcium and making the calcium spikes happen. So that's why we need those hyperpolarizing action potentials to generate the calcium spikes. If we don't see them, we won't get them. Okay? Now when we do that, we get a predominance of IPSPs. IPSPs means inhibitory postsynaptic potentials. Inhibitory potentials from an area of the thalamus called the RNT, the reticular nucleus of the thalamus. Now let's not get that confused with the reticular formation of the brainstem. This R up here refers to the ascending reticular activating system from the brainstem. This R down here is the reticular nucleus of the thalamus. The reticular nucleus of the thalamus is controlling the thalamus. In the thalamus, we need inhibitory control to get the proper balance between excitation and inhibition. We're going to see how important that is in a few minutes. Asleep yet?
Absolutely not.
No, it's great.
On the edge of our chair. Keep it going.
Yeah. My chair actually tipped over.
My ARAS is highly active.
Well, the problem with physiology is if you see this stuff in the lab or in a patient, you get real excited. When you see it on paper, it's not so exciting. It's a little bit dreary, and so I worry about that. And in fact, I say textbooks take the life out of life sciences, you know? And so...
Couldn't agree more.
Yeah, so when I teach, I like to do it in the lab. I like to do it with hands-on, with things happening, with animations. Unfortunately, what I'm talking about here is so theoretical and whatever that you can't do it easily in a webinar with simulations, although next time I will try. Okay, so now that I know that that some of you are awake, let's look at the desynchronized pattern. What do you see here? Where are the hyperpolarizing after potentials? They ain't there, folks. They ain't there because we're in a depolarized resting membrane potential state. We're above the threshold level. We didn't go to that hyperpolarizing level we saw down here, so we don't generate that slow oscillating rhythm. We show a pattern of firing, okay, that is more random. The background is more random, at least it looks more random, and look, the action potentials are actually much more random, aren't they? They're much more randomly spaced, okay, when we see this pattern. So what are the conditions necessary then for a beta rhythm, for example, a desynchronized EEG? Well, now we have to have the ARAS, ascending reticular activating system, turned on, okay, and just the opposite of what we saw before. Instead of increased GK, which means potassium is moving out of the cells, we have a decreased GK, which means potassium is accumulating inside the cells. And that causes, instead of hyperpolarization we saw before, depolarization, which is excitation. Hyperpolarization for inhibition, depolarization for excitation. We don't get those calcium spikes. We don't get those hyperpolarizing after potentials. Okay? And we do get more sodium conductance. Okay? Sodium conductance meaning more depolarization, because sodium comes in to the cell, just like calcium comes into the cell, to depolarize it. But in what we saw before, when the calcium comes into the cell through this GCA, increased calcium, voltage-gated calcium channel, we get the calcium spikes, and they're synchronized. Here, this is a pattern activity that produces the desynchronized rhythm, or asynchronized background inhibition. Now, what does that mean? Remember what we said about the R down here. The R down here is the reticular nucleus of the thalamus, which is controlling the thalamus. And those IPSPs are now more asynchronous or random. And because they're more asynchronous or random, we see a more asynchronized random pattern up here. Okay, now that was the simple part. Ha ha ha. I want to hear a laugh.
I laughed. It was muted.
So did I.
Okay, I need some more acetylcholine for this.
Are we ready?
Yep.
Should we take a deep breath?
Took one already.
Okay.
Yep, we're good.
That was the simple part.
Asynchronizing.
Now what we have to do to understand a little bit about how real life works, we have to kind of try to put the system together. And because of the time limitations, I put it all on one slide. I apologize. I hope it's not blowing your eyes out or your mind by looking at all this. But we're going to break it down. So stick with me. Okay? Now, remember we talked about the high ARAS activity, producing a desynchronized beta, and sometimes also responsible for part of the synchronized alpha rhythm. Okay. We don't know too much about the beta, but we do know a lot about the alpha, because as Richard has said many times, that you QEEG guys believe that the alpha is a pretty consistent rhythm and is more predictable than some of the others, especially in the eyes closed state. And I think the literature, the research, bears that out. So we're going to concentrate here on the balance between alpha and delta. We're not going to focus too much on beta and theta because much less is known about it. But sometimes they go together and sometimes they don't. Meaning what? Some brains are different than other brains. Okay. Now, the acetylcholine dominates. Remember in the earlier slide we said there's a domination of the cholinergic inputs when we have the high arousal state. The ARAS activity is high. Through M1 excitatory and M2 inhibitory, those are muscarinic acetylcholine receptors called M1 and M2 on those pyramidal cells. And this is, of course, the input from the thalamus. And the input from the thalamus is coming from the nucleus basalis, which is primarily acetylcholine. And this is producing or responsible for mainly the high arousal state. So what happens when we move the balance, we move the pendulum from the high arousal state to the low arousal state? Remember we said before, we're going to get less acetylcholine generated and more what? Norepinephrine and serotonin. These are what we call our monoamines. So there's a balance between the cholinergic and the monoamine inputs. And so we get a predominance of slower rhythms, primarily the delta. And now we have lower ARAS activity. They are both awake. These are two awake states. Now, it just so happens, if we get to sleep later or at another time, remember that this delta rhythm is also going to be characteristic, the theta and delta rhythm, slower rhythms, of what we call non-REM sleep. And this faster rhythm that looks more desynchronized like beta, with more cholinergic input, is going to be characteristic of what we call REM sleep. Just put that in the back of your mind for now. We'll deal with that later. we understand, I think everybody understands what arousal means, and I think some of what we're talking about here would correlate very well with the NewMind Academy, the software, the system that you use to indicate arousal, the global measures of arousal, for example, and versus the local, you know, those nice meters that I see all the time. So everybody kind of understands what we mean by arousal. It's not always clear what we mean by sensory and motor here, so I'm going to clear it up. We're used to thinking of motor as movement, and motor still means movement. I'm not changing the definition. But in this case, because we're talking about information coming from the brainstem, we called it ascending reticular activating system. So we called it ascending, going up. We can't talk about motor because motor is efferent information coming down from the cortex to the brainstem. So when we mention motor here, we're talking about the sensory aspect of motor. So I hope everybody realizes that to control our muscles properly, we have things called, or structures called muscle spindles and Golgi tendon organs, which we call proprioceptors. And they let us know about the state of our muscle tone, where our limbs are, where our muscles are with respect to spatial organization out there in space. So we can better control our muscles and our reflexes. We must have sensory input to the motor system. So that's what we mean by motor here. It's the sensory aspect of motor movement from, for example, the Golgi tendon organs, muscle spindles that I said were proprioceptors, and including input from the cerebellum, which we know is the motor coordinating center, that's sending information constantly to the cerebral cortex up here. So this is what? The sensory aspect of motor, the proprioception aspect of motor, not the actual motor movement itself. Is that clear?
Yes, very clear. You need a feedback system of sensory and afferent flow to control yourself, right?
Exactly, exactly. So here what we're talking about is general sensory. Not motor sensory, but general sensory. What we're used to thinking about is eyes and ears and smell and cutaneous senses, touch, temperature, pain, general sensory, as opposed to motor sensory. Okay, so that's why we've included these. And serotonin and norepinephrine, as I said before, locus ceruleus and the raphe nuclei are the generators of these kinds of inputs. So again, we're looking at a balance. Now let's go over here. We have those same inputs coming up, and what they're doing is they're trying to excite the neurons of the thalamus, because these are coming from the brainstem, aren't they? Well, the acetylcholine is primarily coming from the nucleus basalis, which is the thalamus. Serotonin from the raphe in the brainstem, norepinephrine from the locus ceruleus, and in a desynchronized EEG, or high arousal EEG, we have a decrease in potassium conductance. What does that mean? That means potassium is accumulating inside the cell to depolarize or excite the cells. Okay? Now, these are receptors that are coupled to G proteins. And there's basically three kinds of G proteins: a GS protein, a GI protein, and a GQ protein. Here we're only going to deal with GS and GI today. The GS protein increases cyclic AMP inside the cells. Now, what cells are we talking about? These are the cells of the thalamus. Remember, we're projecting up to the thalamocortical neurons that are going to generate those brain waves. Those are the waves. Those are those are the wind that are producing the waves on the sea. And so these are through beta adrenergic receptors. So as long as we're activating the activating system through potassium accumulating inside cells, which are causing potassium channels to close, decreasing the G, decreasing the conductance for potassium, because remember, potassium is always conducted out. So now potassium, if it's not conducted out as much, it accumulates in. And those cyclic AMP, the increase in cyclic AMP that results from that, okay, is associated with stimulating beta-adrenergic receptors. Remember, beta-adrenergic receptors are these norepinephrine receptors. Okay? There are other receptors for serotonin called serotonin receptors. In a subsequent slide, we'll deal with them. But let's just think of the norepinephrine system here. What do you know about beta blockers? There's a group of drugs called beta blockers that would block this, wouldn't it? These are bad beta-adrenergic receptors that would be stimulated. But if we block them, we'd get the opposite. We'd get a decrease in the cyclic AMP, wouldn't we? So we'd get moving from a high arousal awake state to a low arousal awake state as we block these receptors with beta blockers. Now, beta blockers are given when someone has heart conditions, okay? Someone has heart failure. When someone has myocardial infarction, we want to slow down the metabolism of the heart. We give beta-adrenergic blocking drugs. But we also give beta blockers to calm, don't we? To calm. So they have a central action, not just at the heart, but they also have a calming influence on people. And this is the mechanism by blocking these receptors. Less arousal. Okay? There's more than one way to skin a cat. We can also block or have the same effect of blocking the beta-adrenergic receptors through the GI-coupled receptors. Remember, G stands for a G protein. G protein is on the membrane of the neurons. And while the GS protein increases cyclic AMP, I might as well tell you what the S stands for. It stands for stimulate adenylate cyclase. Adenylate cyclase is the enzyme that increases cyclic AMP. And this inhibits adenylate cyclase, the enzyme that makes cyclic AMP, so we decrease the cyclic AMP, and we get an increase in conductance of potassium. Remember what happens when we get an increase in the conductance of potassium? Potassium moves from inside outside, and we hyperpolarize. We get more inhibition. So that's the role of the RNT neurons. Primarily, the RNT neurons in the thalamus are the main source of GABA, gamma-aminobutyric acid, the main inhibitory neurotransmitter. And this is a particular, there's two types of GABA receptors, A and B. This happens to be the GABA B receptor. And the GABA B receptors then are responsible for decreasing cyclic AMP. That's going to have the opposite effect, just as if you would give a beta blocker. And so it inhibits the sensory nuclei, and what does it do to arousal? It decreases the arousal. That's why I have up here, we get a more synchronized low arousal state when we start inhibiting the cholinergic mechanisms. So what starts taking over when we inhibit these mechanisms up here? The mechanisms down here, which are for the monoamines, the norepinephrine and the serotonin. Okay? Making any sense at all?
Yes, it is. Rick.
Yes.
That would help explain why when we inhibit cholinergic receptors, we get more delta, wouldn't it?
Yes, it would. Yes, it would. That's what we call the monoamine balance that you're changing the balance between cholinergic and monoamine inputs.
So when we're watching our clients and they get drowsy during a session, their acetylcholine's going down and their delta is probably coming up.
That's correct. And the delta coming up is primarily an effect of the serotonin we're going to see.
That's a great connection there. Thank you very much.
You're welcome. I'm glad you brought it up. And I'm glad I'm getting a little bit of validation from the guru.
Well, I think you're the guru in this area.
No way, no way. I can't compare to you. Okay, so let's go on. And I know one thing, if I were to compare myself to you, that you're a much better businessman than I am when I look at your business model. Wow, what an amazing business model you have.
It's organic.
I don't think so. Seems like it took a lot of work. And guess what? I've been in several medical related businesses that have all lost money for me. I haven't made a penny, which is why I'm at 71, I'm still working my ass off.
Yeah, but you're on the beach. I'm not.
True. No, I got plenty of room, guys. You can come anytime.
Don't tempt Sean. He may take you up on it.
Oh, Sean, I would love to have Sean. Sean's great. Okay.
Is that
All
a
right.
real invitation, Rick? Is that an invitation?
Yes, of course. It's an open invitation.
I checked the flights, okay?
Yes, of course. Okay, are we ready to go on?
Yes, please. This is great.
Okay, so now if we were to look at those thalamocortical neurons that we said are the main
I think we lost Rick for a second. Hopefully he didn't get this.
other way.
Rob, are you hearing Rick?
Frequency versus high frequency, low amplitude waves, okay? And so generally we speak of the low frequency, high amplitude wave. When that predominates, we're in it, the thalamocortical neurons are in an oscillatory mode versus when they're in the opposite mode, we call it a relay mode when we have the high frequency, low amplitude, or more desynchronized wave. Again, we said that we needed the hyperpolarization to generate the pacemaker for the oscillation of the low frequencies when the ascending reticular activating system was inhibited or off. And that put us in this low arousal state that caused us to generate more of these low frequency waves. And now, up here, we see the conductance for calcium. So there is a spectrum here, a spectrum of hyperpolarization. Here's less hyperpolarization, here's less hyperpolarization, and at the same time, more activation of the voltage-gated calcium channels here, and less activation of the calcium channels here. And then when we get to the point where we have a more depolarized or random input of those RNT IPSPs or inhibitory potentials, we're in the relay mode where the calcium channels are inactivated, and instead of having a high conductance for potassium, we have a low conductance for potassium. So again, it's a spectrum. It's a spectrum. So it's not just a single frequency here, and a single frequency here, and a single frequency here, and a single frequency here. It's a spectrum. So we can actually consider that we're changing the frequency, and with it the amplitude too, as we move from a hyperpolarized to depolarized state. Okay? Again, there is nothing new under the sun in this diagram other than I'm showing it differently. But now, don't get your minds blown because I've added some stuff here.
Rick,
So
before you move, can you go back for a second?
Yes.
I have a question.
Yes, sir.
This is Mark. Okay, we're talking now about hyperpolarized or depolarized or anything in between.
Yes.
Am I correct, assuming that there is another component, an underlining, how much of the total is available? You have explained that these two polarizing chemical substances create actually the activation or deactivation of patterns in the cortex, which we measure. Could I theorize that the total amplitudes depend on how much availability of the building blocks for these hormonal neurotransmitter things is available? Like the total of your graph here, the height of your graph depends on how much building blocks for neurotransmitter the system is able to provide. Is that correct?
I think what you're saying is yes, it would be at least theoretically correct. I'm not sure we have enough research to back it up, but it would be at least theoretically correct. So if you don't have enough building blocks, you're not going to get the amplitudes. And
yeah,
so
that's exactly what I'm pointing at. So that's where the total brain power comes in, right? It has nothing to do with what is polarized. It has the amplitude, the overall amplitudes have something to do with how much the gastrointestinal system actually can produce. That's where digestion comes in. Would that be correct?
I would love if it were that simple. And maybe it is. So
well,
I don't.
Very global on a very high.
Yes, on the global. I said yes. It's theoretically it seems possible. All I'm saying is it's probably not reducible to that, easy formula. It's probably more complicated than that. But it's a good working. How about if we call that a good working hypothesis?
All right. Thank you.
Thank you. So now I've added to this diagram some of the more details, bringing in what we've already talked about to see if it makes sense. We said that when we had high cyclic AMP, we had a low potassium conductance state and a low calcium conductance voltage-gated channel activation state. And that led to what? Low voltage and high frequency, right? Low voltage, high frequency is what we talk about as the faster waves, subserving in the awake state high arousal. And again, we're only talking about the awake state here. Okay? Serving that are the serotonin receptors. And we have 7 different kinds of serotonin receptors, and they're actually numbered, and I numbered them here. Serotonin receptor, 5-HTR stands for serotonin receptor. Number 2, number 3, number 4, number 6, number 7. I underline numbers 2 and 3 because those are channels that are not, those are receptors that are not controlled by G proteins. Those are actually just ion channels. Okay? Ion channels like sodium and potassium ion channels. But 4, 6, and 7 are actually controlled by metabolism. They have to be controlled by the cyclic AMP. So again, the 2 and 3 are independent of the cyclic AMP. 4, 6, 7 are dependent upon the cyclic AMP, but they do the same thing, these 5 different types of receptors. Now look at the serotonin receptors down here. Remember, this is the high frequency, high arousal state, but down here we have the what? Low frequency, low arousal state. The input for the low frequency, low arousal state with the high potassium conductance are only 2 types of serotonin receptors, receptors 1 and 5. Okay? And what are they doing? Anybody remember? If we got high cyclic AMP down here, we'd have to have what? Low cyclic AMP down here. Right? So this is the balance. These are the more inhibitory inputs. We said for acetylcholine, these are your M1 receptors. So we have specific drugs that work just on M1 receptors. And we have specific drugs that work on the M2 receptors. The M2 receptors were inhibitory. This is the acetylcholine inputs in red. In red. You see the red here? So here's the high arousal acetylcholine input, and here's the low arousal acetylcholine input, producing the low frequency and the high frequency here. So again, it isn't quite so simple as having a acetylcholine monoamine balance. It's really also the receptors, because here we see acetylcholine participating in both the high arousal and low arousal state via two different types of receptors. Here we see norepinephrine participating in the high arousal and lower arousal state by different receptors. This is an alpha 1, and there's two types, actually three types of beta receptors, beta 1, 2, and 3. We'll lump them as all beta adrenergic receptors here. Again, serotonin operating both in the high arousal and the low arousal state through different sets of receptors. So this adds a little more complication to the issue. So let's sum up, because I think we're coming to the end, right?
That's correct.
Okay. So again, I have more, and we can continue this at another time.
Well, we'd want to, definitely.
But if we're going to sum up what some of the key ideas that would lead to a ability to apply this clinically, that first of all, we recognize that one of the, and again, I'm not talking about every brain. I'm talking about what's found for most brains, most normal brains, okay? And for most normal brains, or at least we can say for some people, we find that the muscarinic, well, this is true for almost everybody. The muscarinic acetylcholine receptors are a major source, maybe not the only source, major source of the alpha rhythm generation when a person is eyes closed in the resting state. Okay? The monoamine receptors, here's muscarinic acetylcholine, here's monoamine receptors, serotonin, dopamine, norepinephrine, generating the delta rhythm primarily. We find that if we increase delta power, it correlates with decreased CHAT activity. CHAT is the enzyme that makes acetylcholine. Again, showing the balance. Acetylcholine esterase inhibitors. Acetylcholine esterase is the enzyme that breaks down acetylcholine. So when we give acetylcholine esterase inhibitors, then, for example, there are pesticides, there is nerve gas, there are all kinds of toxins that produce this, as well as we have drugs that we use as acetylcholine esterase inhibitors, okay, like pyridostigmine and physostigmine, that these drugs and these chemicals also, you see the balance here reflected in more alpha and less delta, okay? Again, the balance, more cholinergic and less monoamine. When we destroy the nucleus basalis of the thalamus, it's known to decrease the alpha, so that's strong evidence that the cholinergic input is responsible mainly for the alpha rhythm in the state we're talking about. As we deplete serotonin, we get a decrease in delta primarily during slow wave sleep. So what we call slow wave sleep, non-REM, this is a non-REM stage of sleep, we'll talk about it another time, is dependent upon delta, and when we deplete the serotonin, we don't get the delta. So this monoamine balance hypothesis says there's effects of varying levels of acetylcholine versus monoamines. And when there's a relative excess in acetylcholine versus monoamines, we can have more alpha acetylcholine or delta monoamine power. Now sometimes alpha goes along with beta, not always. Sometimes theta goes along with delta. We don't always know that. But in most brains, at least this alpha-delta balance, we know about it and does occur. High relative levels of acetylcholine increase alpha power, whereas high relative levels of monoamines, primarily serotonin, but also norepinephrine and dopamine, increase the delta power. For a clinical correlation, alpha power seems to be a marker, at least in some studies, for sustained alertness, and it's positively correlated with the activity of a network that starts in the cingulate and includes the insular cortex and the thalamus, called the cingulo-insular thalamic activity. We can talk about that another time. and that the acetylcholine receptor agonist, physostigmine, which happens to be an acetylcholine esterase inhibitor, so it causes acetylcholine to build up and stimulate more acetylcholine receptors, increases spatial attention, and that's accompanied by increasing both alpha and beta power. So again, a lot of this leads to some good ability to correlate this balance we've been talking about clinically. It's not new. About 75 years ago, a fellow by the name of Jasper showed that in ADHD, there was a predominance of slow and a decrease in less faster activity. Now we know this as the theta-beta ratio, and many times in our webinars we've talked about how we think the ratios are important clinically. And so this is not a new concept. And however, we're not going to apply it to ADHD because ADHD, there's many subtypes of ADHD, and it doesn't really always follow this theta-beta story. But some more evidence that this balance does in some brains exist and is important. In depression, we get a decrease in delta power, well known. Low monoamines responsible for that. In fact, by definition, depression is low monoamines. Treatment for depression is an SSRI, which raises serotonin and raises the delta power. And guess what? Many clinical studies have shown that if you increase delta power and during slow wave sleep, it's actually a marker for a good clinical response. We have similar things going on in Parkinson's disease and OCD. And I will end there because I know we're 5 minutes beyond and people have stuff to do. So everybody, thanks for listening and peace out. I will see you another time.
Hey, thanks, Rick. I'm just going to say goodbye, everybody, and thank you so much for your time, folks. Neuro at Night Monday, Tom Clora on Wednesday. Have a great weekend.
Thank you.
Yep. Thanks, Rick. That was terrific.
It was great.
Really enjoyed it.
Excellent, Rick. Thank you.
Looking forward to
Think
part
of
2.
questions. Yeah, well,
And we'll schedule part 2.
again, we didn't have time, and people weren't asking questions, but I'll be open to questions at any time about this.
Terrific.
Right.
We'll
Thanks.
do some more next time.
Okay, great.
Thank you, Rick. Goodbye, everyone.
Okay, good weekend. Bye.